So, continuing our discussion on diffusion and diffusion in the solid state, let us first look at the mechanism of diffusion in the solid state, which had been a subject of controversy for several decades. So, here let us consider, let us say, a crystalline solid of, let us say, A atoms, which are arranged in a particular crystal structure. Here we will just take a two-dimensional view of this to understand diffusion. So, one possibility in the solid state is, suppose along with this A atoms we also have B atoms in an interstitial solid solution, which means the B atoms are located at some interstitial site. So, for example, I have a B atom located here. Now, how can it move? So, it has to make a jump from one interstitial site to another interstitial site. So, these are all possible neighboring interstitial sites. So, it can make a jump to this site, it can make a jump to this interstitial site, it can jump to this interstitial site, but it cannot make a direct jump from this interstitial site to this interstitial site. So, for example, it can jump to this interstitial site, making use of the gap between the atoms of A. Similarly, the next jump could be in this direction, a third jump could be in this direction, and eventually the B atom reaches here. So, this is a case where of two-dimensional random walk by the B atoms. Similarly, one can imagine that in the three-dimensional structure, this B atom can move in the third direction as well. So, this is one possibility where the B atom is a lot smaller than the A atoms, and this is what is called as the interstitial mechanism of diffusion. Example of systems where you would have an interstitial mechanism is, one prominent example is the iron carbon system, where the carbon atoms are a lot smaller than the iron atoms, and hence the carbon atoms can diffuse or make jumps from one interstitial site to another interstitial site. A second mechanism that operates in the solid state, again let us consider A atoms with a certain structure. And in this case we have A atoms, and along with we have B atoms which have similar size to A atom, and hence the B atoms are not going to be located in the interstitial site, but they will form a substitutional solid solution. So, some of the A atoms would get replaced by the B atom. Now, if this B atom has to move, it can't obviously move to a interstitial location. That would be that would take up that would require a large amount of energy to get itself accommodated into a small interstitial site. However, what can happen is the following. We all know that in the solid state, all structures for temperatures, for finite temperatures, would have some atoms missing. So, they will have some vacant positions or what are called as vacancies. So, for example, there can be an atom missing here. There could be an atom, let us say, missing here. It cannot jump from here to this vacant site, but this B atom could make a jump to this vacant site and come to this position. Similarly, if there was no atom here, then it can make a subsequent jump to this position, and that is why how it is able to move from here to here in two successive jumps. Very clearly, this would require a vacant site to be nearby. So, in this particular two dimensional structure, around this B atom, where all it can make a jump, it can make jump to its four nearest neighbors if here, here, here or here, provided at least one of them is a vacant site or at least one of them is a vacancy. So, this kind of diffusion, which is extremely common, is called vacancy mechanism. An example of this could be, for example, copper nickel. Copper and nickel form substitutional diffusion or substitutional solid solution, and here if the copper atoms have to move through a nickel crystal or a nickel atom has to move through a copper crystal, it will have to find a vacancy in one of its nearest neighbor positions. Now, in both cases, so these are the two cases by which diffusion in the solid state can be adequately described and then eventually mathematically modeled to be able to determine the kinetics of diffusion, how fast the atoms would move. But it should be noted that for an atom to jump from this location to a vacant site, in the case of substitutional solid solution and in the case of interstitial solid solution, for an B atom to jump from here to here, one should note, say for example, in the case of interstitial solid solution, the gap between these two atoms is actually much smaller than the size of the B atom. In order for this atom to jump, it has to squeeze through the two neighboring atoms, and therefore there would be an energy hill for this atom to migrate from this location to this location. So, it still has to climb an energy hill. Similarly, here as well, even though you have vacant site, all these atoms are quite close, so they will have to move away to give space for this B atom to jump, and again it will have to go through a energy hill for making the jump. The difference in these two situations would be that if B atoms are very few in number, then it will always have a free interstitial site around it. So, it does not have to look for a free interstitial site, it will always have. So, the only energy hill that it has to climb is squeezing these two through the neighboring atoms. On the other hand, in the vacancy mechanism, first there is an energy hill for the jump, second there is a chance whether the site is vacant or not. So, there are two parameters that come in. There is a probability of a site being vacant, that will have to be taken into account, plus the energy required for the jump. So, looking at it this way, interstitial diffusion would typically be faster as compared to the diffusion by the vacancy mechanism. And very quickly, I can show you a simulation of the vacancy mechanism in this slide. Here what you see are the red atoms on the left and the black atoms on the right. They are all the sizes of the same order, hence the only way these atoms can jump into the each other's crystal structure is by a vacancy mechanism, and all the white circles that you see are the vacant positions. Here I have deliberately put a very high density of vacancy. Typically in a solid state the number of vacancies are much less in number, and of course they increase as temperature is increased. So if I look at this and I start the simulation, these vacancies will start to migrate, will start to jump around, and you can see that the black atoms have started penetrating towards the left and the red atoms have started penetrating towards the right. So this is a simulation of the vacancy mechanism in action. We will let it go on. We will see towards the end how far things have changed in this. We had started with red atoms on the left and the black atoms on the right. Now let's look at a quantitative picture of diffusion, that how we can develop relationships for diffusion in order to determine the kinetics of diffusion. So consider a hypothetical crystal in fact hypothetical cubic crystal, in fact I will say simple cubic crystal to keep things simple. So this crystal may have A atoms and some B atoms substituting the A atoms. So let me first draw the picture of this. So I have atoms again put in a simple cubic crystal, and I am only going to draw a 2D projection of the crystal. So let us say this is my 2D projection of lots of unit cells of the cubic crystal. So each one, for example, all I am seeing is one square here, but this is, you can imagine, a unit cell here with atoms located at the corners. And of course you can you will have on each of these atoms on the top as well, and of course atoms at the bottom. Let us consider, and let me also put some B atoms in this. So these white ones are A atoms, and let us put some B atoms. Something like this. And the way I have drawn it, there is some kind of a concentration gradient. So there is a higher density of B atoms on the left, and as we move towards the right, the density of B atoms is reducing. If these B atoms are given a chance to jump, then in the end this crystal should become homogenized, where B atoms are uniformly substituting the A atoms all along the crystal block. So let us look at this concentration gradient. So this is the distance we move, x. This is C, the concentration of B atoms, measured as number of B atoms per unit volume, or it could be moles per meter cube. And let us look at two atomic planes. So, this is one atomic plane, this is another atomic plane, and let us say this is how the concentration varies with distance, a straight line. So, I have here let us say location x, this is location x plus delta x, concentration, let us say this is plane 1, this is the atomic plane 1, this is the atomic plane 2. So, the concentration at x is Cx, concentration at x plus delta x is Cx plus delta x. Now, consider any atom on plane 1. For example, suppose I consider this atom. In which directions it can jump? How many directions are possible for it to jump? So, one has to look at what are the nearest neighbors of this atom. This being a simple cubic crystal, its nearest neighbor on this plane is this one, this atom, this position, and so there are 4 positions here. There will be a 5th position on top, there is another atom at the top, and there is another atom at the back side of it. So, there will be total of 6 positions. It can jump to any of these 6 positions provided there is a vacant site available. Now, I want to find out overall what is the flux of B atoms jumping from plane 1 to plane 2. So, flux of B atoms from plane 1 to plane 2. The flux of B atoms from plane 1 to plane 2 could be written like this. First, let us see the units incidentally for flux would be number of B atoms per unit area per unit time. Per unit area per unit time. Let us say we are looking at a unit cross section of unit area. Then the volume that is in between plane 1 and plane 2 is simply delta x, the area of cross section being unity, multiplied with Cx, the concentration, which is number of B atoms per unit volume, are the total number of atoms, B atoms on plane 1 per unit area of the plane. So many atoms can jump from 1 to 2, but of course not all of them are going to jump. So there is a certain jump frequency, that this is the rate at which B atoms are jumping. So let me call that frequency as nu prime. This is exactly the same jump frequency that I had used in the random walk problem of the last lecture. So this is the total number of jumps per unit time per unit area of B atoms in plane 1. However, not all jumps will take a B atom from plane 1 to plane 2. Some of the jumps, for example, if this is the atom I am considering, it can jump here, it can jump here, it can jump here, it can jump here, it can jump at the top atom or at the bottom atom, total of 6 possibilities, out of which there is only one possibility which will take this B atom from plane 1 to plane 2. So out of total of 6 possibilities, only one possibility will move this atom from 1 to 2. Hence, the probability of an atom jumping from 1 to 2 is 1 upon 6, and of course this jump frequency which would take into account the position being vacant, etc., would also be there. We are going to talk about more in detail regarding the jump frequency later. So, this gives me the flux from 1 to 2 of B atoms per unit area per unit time. Now, similarly, B atoms can jump from plane 2 to plane 1 in a similar situation. In that case, the total number of atoms available per unit area is Cx plus delta x, the concentration in plane 2 multiplied by the volume would give me number of B atoms in the plane 2 per unit area, multiplied again by the jump frequency and multiplied by 1 upon 6, because again there is only one jump which would take an atom from plane 2 to plane 1 out of the 6 possible jumps. Hence, this is the flux of B atoms per unit area per unit time from 2 to 1. So, I have now flux of B atoms going from plane 1 to plane 2, I have flux of B atoms going from plane 2 to plane 1. Out of this, so what is the net flux? So, net flux in the positive x direction. So, the net flux in the positive x direction, let me call that as J, then clearly this is J1 to 2 minus J2 to 1. If I write this, so this is simply 1 by 6 nu prime Cx delta x minus 1 by 6 nu prime Cx plus delta x times delta x. This is equal to, and let me write it, rearrange it a little bit, and let me write it like this, minus 1 upon 6 nu prime delta x times Cx plus delta x minus Cx. If I multiply and divide by delta x, then I have this. This term is nothing but the slope of this line. And the slope of this line can be simply be written as dc by dx, or the concentration gradient. Hence, the net flux becomes minus 1 upon 6 nu prime delta x square times dc by dx. Let us look at this term. And in fact, before this, let me also replace, let us write the jump distance, write lambda as the jump distance instead of delta x. Okay. So, replace this delta x by lambda square. So, lambda is this delta x, or this is nothing but the distance between atoms, and I have been in the last lecture also I had taken lambda as the distance between the atoms. So, I have just replaced delta x with lambda. This term in circular brackets has a jump distance squared multiplied by the jump frequency, and this we would call it as some kind of a parameter d, which is what is known as the diffusion coefficient. So, from here the net flux is minus d dc by dx, and this is called as the Fick's Fick's first law of diffusion. Note the negative sign here and note the slope of this line. The slope of the line is minus, and this minus will become plus, and the flux would be in the positive x direction from higher concentration of B atoms to lower concentration of B atoms. A little bit about units in this equation of Fick's first law. So, this is my Fick's first law. Flux is equal to minus d dc by dx. If you look at it, d itself we have written as 1 upon 6 nu lambda square. This has units of distance square per unit time. So, typical units for d diffusion coefficient is meter square per second. If you look at units of this, this is number of atoms per unit volume, the number of atoms per meter cube, and this itself is meter. So, the units of dc by dx is meter to power minus 4. And if you look at the units of this, clearly we have the put the units for d, put the units of this, the units of flux J is simply meter square per second. So, number of atoms moving in a certain direction through a plane of unit area in 1 second. Finally, let me reconcile with what we had done in the last lecture. In the last lecture, the diffusion distance, if you recall the relationship, we had written this relationship as x bar is equal to lambda square root of nu prime t, and here the diffusion coefficient is 1 by 6 times nu prime lambda square. So, from here I can write nu prime as 6d upon lambda square. We substitute in this the diffusion distance x bar becomes lambda square root 6d upon lambda square times t, or simply x bar is equal to square root of 6 dt. Now, this factor of 6 is coming simply because we have taken a simple cubic crystal. If we had taken some other crystal, this factor would be different. So, in general, the diffusion distance x bar is proportional to square root of dt. This is also an important proportionality that keeps cropping up whenever we have diffusion. So, in this lecture, I have introduced the Fick's first law. We will go ahead with this and continue our discussion in the next lecture and introduce what is called as the Fick's second law. Thank you.